And we'll say, hope we're all enjoying this. As our inboxes slowly fill up with unread messages. But very nice to have so many talks.
Okay, thank you. All right, so my goal, I guess is the last talk about quantum error correction, is to just draw some pictures. I just really want to get a nice intuition as to what information-theoretic quantum error correction looks like. Because I think there's actually a lot one can say about error correction if you just take just an information-theoretic perspective. So I'm going to not really think about decoding or encoding or what those maps look like, and just try to understand what it means from just information. So to start off with, maybe I should say what I think classical error correction looks like. And to me, it looks like this fruit called a custard apple, which is really good fruit, which you find in India. It's actually originally from Latin America. And it's got these, there's these little seeds in it. And then each seed is covered in this little packet of delicious fruit. And they just nicely pack themselves. And that's exactly the drawing that Mary did on the first day, right? Which is that you just have this picture. And what does it tell you in classical error correction? It says that, okay, I have these points, and they all have these balls of some distance around them, and there's no point within it. And that's the picture. And, not necessarily efficient to encode or decode, but you certainly have all the information theoretic perspective. Okay, so then you might ask, what captures quantum error correction? And I didn't know. So what I did is I opened up Nielsen Chuang, and I tried to see if there was any diagram that vaguely resembled something that I could say. And here's what I found. So I ended up finding this picture. And this is what, in Nielsen Chuang, they claim quantum coding looks like. So the top one's supposed to be a bad code, where the Hilbert space on the left gets sort of mapped into these Hilbert spaces that sort of overlap in some weird ways. And the bottom one's supposed to be notion of a good code, which is correctable. But I wasn't exactly convinced that this was the right picture, because it seems to miss something which I think confuses a lot of people who come from classical error correction, which is that the whole point was that the errors were supposed to be continuous. Right? The whole point was that in quantum mechanics, everything's moving around. It's not exactly discrete. So how does this picture here capture a notion of continuous errors? And all the previous talks this week have all just talked about bit flips and phase flips, and sort of said, okay, that's sufficient. If we talk about these things, it makes everything work out, and let's not worry about all the other types of errors. But maybe what I want to do today is that what I want to show is I want to make sense of what this picture how it should come to be, why it's probably the right picture for what quantum error correction looks like, and moreover, where the continuous errors sit in this place. Okay. So what's my outline for today? The primary goal is to explain the Nielsen Chuang diagram. That's what I want to get to. If I get that, I'll be happy. Then what I'll try to say is maybe a little bit what are called the Knil-Laflamme conditions, which are sort of a mathematical way of capturing what it means to be an information-theoretic error correcting code. And then we'll go on, and then we might talk about the complexity of code states and some QLTC stuff, but possibly. Okay. So classically, right, you just think of these 2 to the k disjoint Hamming balls of radius d on n Boolean hypercube or higher dimensional space. And if you just want information theory, you don't have to make any assumption on the structure. But if you don't make any assumption, then you don't get any decodability. And that's about the entire picture in the classical setting, which is you just have these things. Right. And your encoding map is just a bijection from k-bit strings to the centers. And if you have an error, you just don't really leave the ball, because you're just a finite distance away from the center. So decodability is possible just trivially. So what's the quantum analog? Well, like I said previously, you have these discrete errors classically, but you need to deal with continuous errors. Okay. So in order to do this, I need to sort of come up with a way of drawing high-dimensional space that has enough details that we actually can say what we want to say about error correcting codes. And so this is my picture. it's inspired by the one from Nielsen-Chuang. So here's the idea: is each of these vectors. For those of you who are not familiar with the quantum notation, each of these vectors are these are all going to be orthogonal vectors, and they're all just going to be a basis. So this is actually a tensor product space, right? And that's why it's sort of drawn as a cube. So this is a direct product space, and these are the vectors in it. So there's some implicit origin, which is kind of drawn, and there's 90-degree angles here. So whenever you see corners drawn in a cube like this, that's to represent orthogonal vectors. And then any vector in the middle, not necessarily orthogonal with the others. So that's going to be like a Hilbert space of 3 qubits, 8-dimensional Hilbert space. Okay, if you can draw the direct product, you need to be able to draw a direct sum. And the way I'm going to draw a direct sum is they're just going to be 2 objects which are disconnected. So if I see 2 points, these are 2 vectors, this angle will always be 90 degrees. So this is a high-dimensional space. So this is really drawing a 16-dimensional space here. Okay, so far so good? Okay, so now to correcting errors. What should that look like? So the goal is we're going to try to get to this picture that we had in Nielsen-Chuang. And here's what we're going to do first. We're first going to talk about just correcting a finite set of unitary errors. So that means each of the errors is just a unitary transformation of whatever state came in, and I'm just going to call those E1 through EJ. That's for now. And then once we deal with that, we'll show what all that leads to. And the goal, our goal today is that we want to get to a point where we sort of see this perspective that we have orthogonal spaces per error. Okay. Any questions so far? Yeah.
All these cubes are like you fix a basis, and then all of these cubes are encoding for that basis. Is it the right thing? How to say?
Encoding for the basis? No. I'm just drawing a Hilbert space. So this drawing here is a Hilbert space, which is a 16 by 6. It's a 16-dimensional Hilbert space, and I've identified this is a direct sum. So this tells you the bottom 8 vectors. That one tells you the top 8 vectors, and then there's the direct product structure.
On the previous slide,
Yeah.
So that's also that's 8-dimensional. But here you're just trying to emphasize they're orthogonal.
Yeah, I just want to draw their orthogonal and that I'm acknowledging this tensor product structure. Yeah.
Does this analogy for unitary errors also work for non-unitary errors, or?
We'll get all the way there.
Great.
We're building up. The whole point is to get to a nice picture of what all error correction looks like through simple drawings. So yeah, we're going to start with the finite set of unitary errors that we want to correct against. And then we'll see what all that buys us. And what's going to the spoiler is that we're going to show that if we can do something about just a few finite errors, then we actually get a large continuous set and channels, all that for free. It all just sort of comes from the same assumptions. Yeah.
So starting with this, the nodes are vectors. Right?
Every point's a vector. So if I draw a vector that looks like this.
I understand this. That's all. So is there some sort of locality that you're assuming? Because 8 vectors are,
Yeah. Sure. It's just to draw this like a 3-qubit space. That probably won't come up with any serious importance. But just you can notice that the bottom side of this cube, all the vectors have their first coordinate being 0. So they're like, that's the ket 0. And then if you flip to the top, that's the ket 1.
So should I think of these nodes that you're going to, or these vertices, as always being a standard basis element or not?
Sure. Yeah. You could think of this as like, what we're going to get to in this drawing is I can think of this as my original k-qubit space that I want to encode. So it's the initial.
On the picture on the right, if I look at individual nodes, they're all basis elements, standard basis elements.
Right. So the encoding map has to be unitary in quantum error correction. So all transformations in quantum mechanics are unitary. So the encoding map is what I'm going to draw here in the middle, which is going to take my blue square to the other center blue square. It's like the ideal encoding. But that itself has to also still stay a k-qubit subspace, a 2 to the k dimensional Hilbert space. So that's what that encoding maps look like. And then we're going to try to see that with different errors, it's going to move to like a direct sum with the original space. That's the perspective we want to get to. But how to get to this direct sum structure is not going to be initially clear. But we'll build up to it. Okay. Any other questions? Okay, awesome. All right, so here's where we're going to get to, hopefully. And let's start with a simple example of a non-code. So this is very similar to the picture in Nielsen-Chuang, where some of the cubes overlap. So why would this overlap be a problem? Well, you can see that if this was this encoding, so we have an isometry that maps the original blue cube under E1 times encoding, which takes me over to this guy, right? And I have another isometry which takes me E2 encoding over here. Then you immediately have a problem because both the orange vector and the red vector in the initial encoding are being mapped to the same point, right? Or mathematically, they're just saying, if I take my encoding and then I apply the error, E1, and I do it again with E2, I get the exact same point. So if I happen to show up with this, if this vector happened to show up, I could not know how to decode it. So this is a non-code. This cannot happen if you're going to be an error correcting code. But in fact, there's actually going to be a stronger statement, which is that if my initial assumption is that the red and orange vectors were not only distinct, but they were orthogonal, then I claim that we should actually see some orthogonality that occurs. So here's what the picture should look like, which is that if I have two vectors here in the initial thing, orange and red, which I'm going to assert are orthogonal, then I claim that in the two different encodings, where the red vector maps here and where the orange vector maps here have to be orthogonal. And this is because of what it means to be perfectly distinguishable in quantum mechanics. Two vectors, or two states, are perfectly distinguishable if and only if they're orthogonal. So if they're orthogonal, then there exists some way of distinguishing the states. And if they're not orthogonal, then the best you're going to do relates to the cosine of the angle between the two of them. Okay, so what does that tell you? So it says you're only correcting these errors if you can distinguish these two things perfectly and you get the orthogonality. But let's note that it would be too much for us to ask for orthogonality between these two states, between E1 times applied to the encoding of one vector and E2 applied on the same vector. Right? And the reason is because if those errors were basically the same, they're two unitaries E1, E2, but they're just off by a minuscule amount, then by linearity of all the transformations, the angle is going to be preserved. Right? So you're not going to be able to get that to correct. But what we'll find is actually for some errors, E1, E2, this could be orthogonal. So we sort of see that if there's some notion of distance between E1 and E2, then we're going to see that the encodings have to also have that error. Have that same distance. But if there's some encoding which is sort of some notion of far or orthogonal between two errors, then we might be able to get orthogonality. And what we're going to see later on is that these errors under which they are orthogonal sort of form a basis for the set of errors you can correct. Okay, questions? All right. Okay, so what's the benefit of this orthogonality? Well, here's what you get, right? So you have these two vectors, this orange and red vector in the initial thing, and we're going to assume they're orthogonal. And then what you'll get, though, is that the orange vector is going to be orthogonal to all the different possible encodings of the red vector, including the one in the error that it occurred. So this orange vector, so this is the E2 encoding, right? So I have this orange vector. It's going to be orthogonal to the red vector because this was an isometry. They were originally orthogonal, so they'll stay orthogonal. And then in every other possible encoding by the previous argument, they'll still be orthogonal. Right? So what do you get? You have that this orange vector is orthogonal to this red vector. So then you can say something even stronger, which is that if the two vectors were orthogonal, then the spans of all the possible encodings and the spans of all the possible encodings on the other side are also orthogonal, which is intuitively going to get us to this idea that if you can correct against the errors E1 through EJ, then you're also correcting against all the unitary errors that are contained in their span. So now we're starting to see that there's some notion of a basis for the set of errors, even though you have a continuous set of errors. In some sense, being able to correct against just some finite set of them really is capturing everything you need. And so then we're going to start to see that it's going to suffice to prove that the error correction properties, you only really need them for a basis. And the rest will follow. Questions? And this is, this is why the previous talks really only discussed correcting bit flips and phase flip errors. And this is because the set of all unitaries can be expressed in terms of bit flips and phase flips, like some linear combination of them. And so if you can correct the bit flips and the phase flips, then you can sort of get to correcting all the errors.
Question?
Yeah.
Where did you use that E, I, J are unitary errors?
I assumed it by assumption. Oh, that we use that for the linearity statements every now and then, right? So whenever I said that distances didn't change too much, I was not only assuming linearity, but I was also assuming unitarity, which means that the vectors didn't suddenly get longer or shorter, right? They just preserve their norms, and moreover preserve angles. So the unitarity was necessary here, just to initially prove that this orange and red vector in the initial statement in this E2 times encoding maintained the orthogonality, right? Because the encoding map, okay, that was unitary. We're fine with that. But unless I assume the error is also unitary here, how am I going to assert this angle stays right angle? So we need it there as well. Okay. Others?
Sorry, so what is the relationship between all the oranges?
Sorry?
What's the relationship between all the orange? I guess when you say one orange and one red are attached to each other, how about the oranges and the coffee, one both copies?
Oh, yeah, I mean, you can make the same argument the other way, right? I'm just saying that since this orange vector is orthogonal to the red vector in the initial space, this orange vector is orthogonal to every red vector here.
Oranges with respect to one another.
Oh, we can't say, right? For the same argument that we just did right here, where that if you have two vectors, just any two vectors, right? They could be close. Yeah. Over the set of errors. Yeah, the red and orange points, they're not special. They're just any 2 points. I just need them for drawings. Okay.
So to be clear, two orange vertices could be the same vector when you encode after the error.
No, we'll actually show that if they map to the same thing, then those two errors were identical, at least acting on that vector. Yeah. Okay. So what you can actually go and do a little bit forward, and I'll leave this as an exercise, is you want to say that we actually can sort of get a basis for the set of errors, which is this idea that if I have two errors, which I'll call E1 and E2 now, and I say this red vector gets mapped over here, and then under E1, and then under E2 it gets mapped over here, and then I sort of have this angle here between the two encodings, between A1 and A2. And then what you can show is that whatever this inner product between A1 and A2 is, so this complex number, which I'll call, I should have called it at 1, 2. And this, you can actually show is that it's going to be an invariant that only depends on the errors themselves and not which state. So no matter which state you started off with in the initial cube, if you were able to correct the errors, then this angle must have stayed the same. That's the exercise. And the hint is you just need to use the unitarity property. Okay. So then why is this going to give you a notion of a basis for the set of errors? Well, if you can correct all the errors in some curly set E, you could just first think about, let me take any vector A, and let me think of what the span under all the errors would be of E applied to encoding of A. And that's going to be a vector space, a basis space. And if it's a vector space, then there's a basis for it. We're all just dealing with finite dimensional vector spaces here. So then I can find a basis for that, and all those basis vectors were of the form some encoding, some error applied to encoding. So then I'm going to get this E1 EJ, right? So I have that these, I have that these E1 through EJ necessarily exist, at least for the vector A. Okay, but what you can show is by that exercise that if you did this for any other vector B, same thing occurs. right? The same E1 through EJ have to form the basis. So that's also not exactly obvious, but it's not too hard of a linear algebraic statement to argue. And then this just gives you a natural notion of a basis of errors. Because you could define now an inner product on these errors, which is that E1, EJ, the inner product between them is just going to be whatever that eta ij coefficient was, which one way to look at it is you could take any A and just think about what this calculation is. And it's going to be the same calculation every time. And you'll get a notion of inner product between the vectors. And so the basis for the set of errors that we want is going to be a basis with respect to this inner product. Okay, so that tells you sort of there's a basis for the errors. But now what happens with those errors that sort of are, somewhere in between the basis vectors? Well, let's take two errors, E1 and E2, which are going to be orthogonal. So I'm just insisting that because I'm going to say that the encodings of some vector, this red vector, are orthogonal. And now let's consider this sort of pink error that could occur that's somewhere in between the two, right? So we know how to correct if we were in both of these direct sum spaces. But what do we do in the middle? So yeah, in reality, I probably should have drawn this so this pink one sort of overlapped both of the purple cubes, but I thought it would get really messy. And so, but the idea is that because the two purple vectors are purple errors are orthogonal, because these two are orthogonal, they form a basis for the set of errors, and we could measure against that basis, right? They're perfectly distinguishable. So what we'll do is that if we actually had this pink error state and we measured according to that basis, the error would collapse to either the one or the other, and it collapses proportional to the angle. So if the angle is theta, it's going to collapse to the top one with sine squared theta and collapses to the bottom one with cosine squared theta. So we get this nice thing that, if you can correct these errors, is actually there's a way to correct all the errors in the continuous space just by first measuring, which it gives you this decoding procedure for the continuous space of errors from the decoding procedure for the basis, which is a priori sort of strange. And I think this highlights a strange phenomenon in error correction that is not too often recognized, which is that the way you sort of do a generalized error correction procedure in the information theoretic world is you measure the syndrome, which means it's equivalent to just collapsing that continuous error to a basis error. And the syndrome is just the name of whatever basis element you got. And then you correct the error based on the syndrome. So error correction is, it composes of two parts, where the first one is non-unitary and therefore destructive. You actually lose the information. And the step two is the information preserving step. It's the unitary step. But in some sense, that should make sense because, you sort of had the information you started off with, and then you had all this accidental extra information you accrued because of the error. It just, piled on. And by doing this destructive measurement, you deleted all that. And you got back to only the information that you really wanted, which is the original information you had encoded. So it's, in some sense, the error correction, you could think of it as a controlled destructive process. Okay, so that should get you to the perspective where if you can take these errors that are basis elements, they have that orthogonality condition we suggested, then you actually get a direct sum decomposition of the space. You're going to get that whatever my original encoding was, if I apply that error E1, it's going to yield an exact copy of the original space, and it's going to be in direct sum. The next one's going to be in direct sum as well, and you get a decomposition of your entire space in terms of this. And then there was a question about correcting channels. You can always correct an error channel whose elements are parts of this because they're just a probabilistic mixture of the unitary channels. So, are there any other questions? Yeah.
So, a lot of physical errors I imagine are something like decoherence, where your cube becomes a sort of squashed cube where you lose distinguishability. Somehow that won't fit into this setup, right?
So yeah, It will, because the decoherence you can sort of think about as a linear combination. It's not a unitary transformation, right? So then you have to sort of first break it up into its unitary components. So we'll get to that in a second when I describe how to think about erasure errors from this perspective, which is sort of be a generalization of some decoherence. Other questions? So what's our picture? So classically, we had that all the words that correct to A are sort of the ball around A. And then quantumly, what you have is that it's a subspace spanned by that vector. Anything in here, there's some error that you can correct, because we said you can always correct errors if they're linear combinations of the errors you already knew. And it's this entire subspace. So that's the same analogy of the ball. So that's maybe how you see the quantum picture. Okay. But this gets you something very exciting, which is it gets you to sort of a mathematical definition of being able to correct errors. And that's what we call the Knil-Laflamme conditions. And what they are is that they mathematically capture just all those orthogonality conditions that we drew in the previous cartoons. So the idea here is that to describe it, you say that if I have a quantum code, it's the image of the encoding map. So it's just the blue square on the right-hand side that we previously had. And you think of the projector onto the code as just some matrix pi. And then what you can say is that the code corrects against errors EI if this equation holds. If pi applied to EI dagger, E1 dagger, E2, pi is equal to the coefficients we actually extracted out previously, the inner products between the errors. And why is this the case? Well, you can show that it's not too hard to show that this is equivalent to the following statement, that any two vectors I had in my initial space, A and B, if I look at the inner product post-errors of those vectors, that's going to be the equation on the left, right? Because this here, this is the encoding of B, and this is the error EJ applied to that state. And on the other side is the same thing, except the error EI is applied to the state A. Well, what I should get is that it's just the inner product initially, whatever the inner product was in the original space, times the inner product between the errors. And you can formalize this, and you can try to, if you want to read what the exact recovery operator is, you can read the version of Nielsen-Chuang. But I really think that just the pictorial argument entirely captures this notion. Okay, so what my claim is that this equation here is actually super powerful, and it captures everything you want to say information theoretically about error correction. And we're going to notice some nice properties that come now that we've derived that this equation must be true. So far, we haven't even talked about any instantiation of a code. We've just said that if you can correct against a certain set of errors, E1, EI, then you must satisfy this equation. And we sort of said it's necessary and sufficient, although we didn't really work out all the details. Okay. So now let's sort of put a little structure on what those errors EI might be. And let's just say you want to correct against all the errors of size D. What does that mean? It means that the error you can think of as some unitary that acts on just D of the qubits, tensor identity on the rest of the n minus D qubits. And the punchline here is that if you wanted to correct all the errors of size D, this is equivalent to correcting all the Pauli errors that are possible of size D. And it's equivalent to even correcting just the bit flips and phase flips. Although I always forget if there's like a D versus D over 2 adjustment that needs to be made, but something like that. Okay. What's not so trivial is that it's equivalent to also correcting all the erasure errors of size D. So what is an erasure error? One way to think about an erasure error in the quantum mechanical world is that it's the product of an information destroying channel. So you apply this channel, which completely destroys the information and just replaces it with the maximally mixed state. And the information destroying channel can be expressed as a linear combination of Pauli channels. And so this error is contained in the span of the Pauli errors. So if you can correct against the Pauli errors, you have to be able to correct against the information destroying channel, because it's just a probabilistic combination of the Pauli errors. So you can figure out which Pauli error occurred, correct it. Okay. So this yields you to this property that correcting D-size errors is equivalent to correcting d-qubit erasures. And so this gets you to, I think, the first point, which is worth differentiating quantum codes and classical codes, which is that information in quantum codes is not encoded locally. Because locally, if there was information contained, it's going to violate the no cloning theorem. So we'll see that in a second. But what it says is that if you look at a quantum code and you just look at a few of the qubits, you'll never know which quantum state was being encoded. And if I don't say this in a future slide, I'll just say it right now, which is that this is not a property of classical error correction. Like, think of the repetition code, where you encode the value 0 in n zeros and the value 1 in n ones. Any one bit you look at of the encoded state tells you which word was encoded. But that won't be the case here. In fact, whatever quantum code has, you won't find information locally. Yeah.
I guess just as a clarification, I think nowadays people always, when they say erasure, they also mean you know the location.
Yeah.
So if I have like information destroying, but I don't know the location, the number of errors I can correct is much less than if I know the location.
That's true. I'm just going to say that if you can correct the Pauli's generically of size d that are anywhere, the Pauli errors could have occurred anywhere, then you can also correct the information destroying channel, even if you didn't know where the error occurred.
That I agree with.
Okay.
But I'm just saying that lately there's been a lot of work showing that if they are erasures, you can actually correct errors up to way more, right?
Sure. Yeah. That's probably true. Yeah, definitely true. Okay. And how would you prove this? Well, imagine there was an error E. Imagine the first d qubits of the encoding of x1 and the first d qubits of the encoding of x2. So those are, I'm going to call those states psi1, psi2. Let's imagine those states were distinguishable. Okay. So if they're distinguishable, there's some matrix, and they're de-distinguishable. It means there's a distinguisher which acts only on the first d qubits. What does that mean? It means that mathematically there was some unitary E of the tensor product structure, E prime tensor identity on the rest, so that E distinguished the two of them, meaning that these expectations were different. Okay, but those expectations can't be different because psi I is an element of the code, so I can always toss in a projector onto the code for free, and that's not going to change anything. But then this right here, this is just the Canil-Laflamme condition, and I'm going to get that the value is at a E, and it doesn't depend on which state psi I. So I exactly get that the reduced density matrices on d qubits are exactly the same. A second proof that's probably maybe a little bit more intuitive comes from the no cloning theorem, which is you want to sort of say that if I had an encoding map that looked like this, so here's, I'm going to draw it now, I have 2 qubits, I encode them in all these qubits, and here's a d-sized region. Imagine I just applied the recovery map on the orange region. So I'm able to recover it, right, because it's a correctable error. I get back to the original state that I started off with. But if I just let this guy stay there, I just get the original state. So then I get that if whatever was resulting in this state depended on the original state, then the total transformation was either nonlinear, it is nonlinear, and therefore it violates the no cloning theorem. So this property that within the code space that you cannot distinguish locally is well known as local indistinguishability, and it's a very powerful property because we'll show that it actually proves that the quantum states themselves in the error correcting code have to be complex, have complex entanglement. Okay, I think I said this for the repetition code just a second ago, but another code classically where you can do much more is the Hadamard code, where any bit of information about the code can be extracted from 2 bits of the code word. So if you had encoded the state x and you wanted to know a.x, for example, then you could just pick a random other point B and just look at b dot x plus a plus b dot x, those two sites, and extract the value. So information there is not only locally encoded, but it's sort of encoded in multiplicity, right? There's many different ways to extract out the same information that you want from points. That is not going to be the case in the quantum setting because of the no cloning theorem. So local information cannot be encoded in such a way. And therefore, information is sort of held in these sort of global properties of the entanglement. Okay, maybe a few other applications past just correcting errors is you immediately can get some notion of cryptography or secret sharing just because of the fact that information isn't held locally. So if you encoded a state into n qubits via some code and you divide it into m pieces, where the pieces were small enough that they were far less than the size of the distance, then the number of pieces you'll need is kind of large to recover the state. Okay, and then what we'll say now is this entanglement complexity, which is to prove that there are states which require a large circuit depth to generate. Questions? Yeah.
Is this local indistinguishability property weaker than error correction?
Yes. So the cat state, which is the superposition of all zeros and all ones, so it's just all superposition of all zeros plus all ones with like 1/√2 factor. If you took that cat state, but you also had a phase, so it's all zeros minus all ones, you'll get that these two states are locally indistinguishable up to size n minus 1, but they don't form an error correcting code. Local indistinguishability is not just a quantum property. Like classically, distributions can have local indistinguishability as well. So if you look at the distribution over binary strings of even Hamming weight and the distribution over binary strings of odd Hamming weight, they're also locally indistinguishable because any reduced region just looks like noise. So there's a classical analog to this idea that states have complexity, which is that the uniform distribution over a good code, and I won't exactly specify what good means, and all the possible image distributions of AC0 circuits, so short quantum circuits of arbitrary fan-in, these are statistically very far apart. So you could never have generated the uniform distribution over a code via a short AC0 circuit. And this actually is a stronger statement than the encoding depth of that circuit, of any classical code. Because if you could encode in short depth, then you can also generate the uniform distribution just by pushing through randomness through an encoding circuit. So it's a slightly stronger statement. So quantumly, we're just going to prove that every code state, which is the output of the encoding circuit, requires depth at least log d, where d is the distance of the code to generate. And key difference is that classically you can talk about AC0 fan-in circuits because they have unbounded fan-in as well defined with classical information. Just quantumly, that doesn't really exactly make sense. So we're just going to talk about circuits of bounded fan-in, like depth 2. And the classical intuition comes from what you call noise sensitivity, which is that short depth circuits have the property that if you take a value x and you take a little noise, the probability that the function switches values for a Boolean function with one output is actually pretty small. But what's the problem is with codes is if imagine f was sort of a sub part of my encoding circuit, well, it's going to have the property that if I take two values which are different and I encode it, they have to move very far apart. They have to move like distance d apart, right? So most of the coordinates have to change. And that's just not going to happen due to noise sensitivity unless the depth is large. The quantum proof, I'd argue, is also just simpler. And it comes from the following idea, which is if the state encoding of A had depth t, so if there was any state that was in the quantum code which had low depth t, then you could distinguish that state from some other state B, which was orthogonal in depth t plus 1. So being able to construct the state is necessarily harder than the distinguishing problem. And why is that the case? Well, you could just run the circuit in reverse. So if you ran it on reverse on A, right, you just get you'd take the encoding of A and you'd undo the encoding, so you get all zeros. And if you did it on B, you're going to get this state. But linearity says that if A and B were initially orthogonal, then this vector and this vector are also orthogonal, which means that you must have this orthogonality here. So there's some qubit which could be measured to prove the to show that they're orthogonal. They can't be perfectly distinguishable.
Sorry, can I ask you a question? So you're assuming that T is larger than the size of the qubits, right? Like, I need to take n steps to measure all of the qubits, or it's actually worse than that because I need to like run this repeatedly.
No. I'm just saying there must be some qubit, right? Consider if this.
So you're not worried about the complexity of that task, right? In practice, it still could be very hard to distinguish this from.
Sure. I'm just saying that if you could distinguish in depth T, then there is a way to distinguish in depth T plus 1. Because think about this vector. If this vector here is orthogonal to the all zeros, it must have it's entirely supported on vectors of Hamming weight 1 or bigger, right? So there's some at least one of the qubits has a measurement probability that's non-zero.
Right. Okay. I'm just, it's not obvious to me how I should think of that as a depth 1 circuit because that probability could be arbitrarily small, right? It's like 1 over n or something.
It is, but we're just talking about perfect distinguishability, so that's okay. And this is not about uniform circuits, this is about non-uniform. Any other questions? So from this result that, if you had these encoding states of low depth, then distinguishing takes just one more depth. It says that if you wanted to prove, the encoding states have large depth, then it satisfies to show that there's no way of distinguishing in depth less than log d. And to do that, all you need is this local indistinguishability argument, because if there was a depth T distinguishing circuit, it looked kind of like this, right? You take in a state over here, you apply the depth T circuit, then you measure and you distinguish. Then you look at the back light cone of that state, and it's going to imply that there was an observable of size 2 to the T that could have been measured on the initial state. But that says that the information to distinguish the state was of size 2 to the T. And so as long as 2 to the T is less than D, that's impossible. Gives you the lower bound. It's crucial to say that all the arguments we've made so far have assumed nothing about the structure of the code, other than the fact that it has distance D, and at subtle points we assumed that it encodes at least 1 qubit. But other than that, we didn't make any other assumptions about the code, nothing about it being CSS or any structure. These are just the properties that are inherent in quantum error correction. So if you want to say more, if you want to understand how to talk about approximate code states or low energy states of the code, you're going to have to do slightly more. You're going to have to start making some assumptions about the structure of the code, which will be inherently necessary because of, our arguments really strongly relied on perfect distinguishability. Questions? So one way you could do this is a theorem that I proved with Anurag Anshu and Nico Brookman, which said that for all good codes of energy low with respect to the code Hamiltonian, they require log depth circuits. But crucially, in order to get there, we had to sort of understand the notion of good codes, and we had to look at specific structured CSS stabilizer codes in order to get that. I don't know how to make this sort of statement for a generic family of codes without assuming a considerable amount of structure of the code. But with that, maybe it's also worth saying a little bit about what the picture for CSS codes are, because although the picture for generic information theoretic codes is nice, it might also be of value to sort of understand the very specific case that we think so heavily about. And at first glance, you might think of it as like you just have the same picture of the 2 custard apples, just one for the 2 codes, right? Because the CSS codes are defined in terms of 2 classical codes, CX and CZ. But I argue, and I spent a lot of time trying to come up with the right fruit analogy for this, is that the right fruit is actually a blackberry. And the reason a blackberry is because it's the only fruit actually where what are called drupelets, which are the little sections of a blackberry, have multiple seeds. Like raspberries and salmon berries and all the other berries, each of these things only have one seed in them, but blackberries are the only fruit with like multiple of them. And the multiple thing is key because if you look at the classical codes that you need to form CSS codes, they look a little bit like this. There are these balls, but within each of the balls, there's actually tons of little code words. And I think Nico's talk stressed this, that you have to have all these little code words that are very close to each other. The actual distance of the codes CX and CZ by themselves, the classical codes, is terrible. It's a constant. But you need that, in order to get the quantum code, this is actually necessary. Why is this necessary? It's because the drupelets that form in the code are related by adding the CZ perp code. So there's a picture. This is the picture for CX, but there's an identical picture going on for the CZ code. And each of those points is related by adding that code. And because you needed this like hx hz perp is equal to 0 for the CSS code condition, if you're talking about the quantum LDPC codes, you must get that the distance between elements within this druplet is constant. So you actually have that you have these like little, many code words that are occurring. But then the fun part is while there are lots of these points that are short distance from one another, they form these natural drupelets which have this distance from one another. So maybe this is for CSS code, they really look like blackberries, and I don't think there's any other fruit or object with this kind of property. But there's actually even more structure. Because if you take a quantum code state for the CSS code, and you measure that code state in the X basis, you will get an outcome, which is a code word. So the measurement, if you measured every qubit in the standard basis, it's going to give you a bit string, and that bit string has to be one of those code words. The same is actually going to follow if you did the CZ code, but you have to make the Z measurement, right? Okay. And secondly, there are these logical bit measurements. If you measure the logical bits of the code, they form these separating hyperplanes that divide half the drupelets on one side and half them on the other side. And what you're going to see is that this lets you use a very nice uncertainty principle of quantum mechanics, which is you can take the logical bit flip and the phase flip for the first qubit of the code. The nice thing about CSS codes is that logical bit flip is just a tensor product of the X matrix on some of the qubits, and the phase flip is the tensor product of Z on some of the qubits. And if you consider those two matrices, they have to anti-commute because they're the logical operators for that first qubit. And so they have this uncertainty principle, which lets you tell that the variance of the two measurements, if you measure it according to that operator, the variance of the measurements is at least 1, the sum of the variances, which tells you that in one of these two pictures, if you were to make either the X measurement or the Z measurement, you're going to get some sort of uncertainty principle, that some fraction of the time the measurement has to be on this side of the picture, and some fraction of the time it has to be on the other side of the picture. The measurement is not dominated on one side or the other. And you can't really say whether that occurs for the X measurement or the Z measurement, but you can say existentially that one of those two measurements has this uncertainty principle. And where is that coming from? Well, it actually comes from the fact that this argument works no matter which code state you're arguing about. For a specific code state, you can actually always figure out whether it's the X measurement or the Z measurement or both. That will be uncertain. But if you generically told me I have a code state, I can't say which of those two measurements will be uncertain. But this lets you, this very nice property, which lets you argue about the robust complexity needed to prove NLTS. Okay, maybe I should take another second to take any questions before we go. And maybe I shouldn't even talk about QLTCs, but if there are too many questions. The questions? All right, so let's talk a little bit about quantum locally testable codes and sort of what the picture might look like for that. So in order to talk about quantum locally testable codes without assuming anything about the CSS structure, we need to sort of get to defining a notion of syndrome for error correction. And what we can do is we can take a basis for the set of correctable errors. It doesn't have to be the basis you wanted for CSS codes, because we want to say this for all codes. And you consider a basis. So here's the trivial error. Here's like all the different errors. What you want to do is, if you're encoding k qubits into n qubits, then there will be a basis for the errors of size 2 to the n minus k. And what you do is you label each of the different errors by some bit string, and it can be longer than n minus k. You can give it a label with redundancy, and that label is the syndrome. And the syndrome sort of delineates now there are elements of the basis which are on one side versus the other, right? And then the weight of the check, the ith check, will be the definition, will be the minimum operator, any operator, the number of qubits that operator mi acts on, which distinguishes these two bases. It will be all the basis elements where the value of the ith check is 0, and all the basis elements where the syndrome name is 1 over here. And we know that such an observable must exist because everything's orthogonal. All these basis elements are orthogonal, so it exists. The art really in QLTCs is would be to create operators of low weight, which tells you that some syndrome labelings are better than others, and that's really where you're going to have to do some work. So,
So you see check here. Is there a stabilizer?
No, it's just some measurement which outputs 0 on all the vectors in the left set and outputs 1 on all the vectors in the right set. It doesn't have to be a stabilizer. Stabilizers have equal number of eigenvalues that are +1 and -1. It could be something more general.
It distinguishes one of the values.
Yeah, by size of the observable MI, is that just the number of qubits?
Yeah, so MI can be expressed as acting on these qubits and then tensor identity on the rest of the qubits. Okay. So what is a quantum LTC? A quantum LTC is that you'd say a code is rho locally testable if the expectation over the observable MI, the probability that it detects it, is at least rho times the distance, where the error E is of size delta. So if the larger your error is, the more detectable it is. A random check must detect it. And if you could get rho to be omega of 1, that would be optimal.
By the size of error, you mean the weight of polys?
Yeah. Okay, so there's some results best known, but we don't really have, we don't know how to create rho equals 1 with also good weight and good distance. So there were these constructions that had constant soundness, but the check weights and the distances were lacking, right? So maybe let me say a little bit about just why are quantum LTCs hard to construct. Classically, you can create a very simple LTC in 5 minutes, which is you just take the repetition code and you add random checks. That forms a locally testable code just for the repetition code because of the expander properties of a random code. And inherently, expansion is sort of crucial for constructing locally testable codes. Classically, you have, you can think of this expander example or the Hadamard code, very high expanding objects. But in quantum mechanically, expansion is going to place a limit on the local testability of a code. And to emphasize this result, there was a proof by Aharonov and Eldar in 2013 that said that if your quantum code is sort of small set expanding and it's epsilon optimal, I'm going to speak very highly, then it implies the soundness is bounded by epsilon. So the better you are at expanding, the worse the soundness of your code is. And this is coming from this interplay of this local indistinguishability property, no cloning theorem, along with expansion. And it implies there's some sort of, if quantum locally testable codes exist, they have to come from some sort of Goldilocks regime of expansion. Yeah.
For these examples of QLTCs that you're mentioning, is this just for encoding like a single qubit, or a rate for these sorts of things?
Oh, I don't remember.
But it's like we don't really care about the rate. It's like even encoding 1 qubit is already meaningful if you have good distance.
I think so.
Yeah.
Okay. So, sort of the rough idea of how that argument goes, that if the expansion is, the better the expansion gets, the worse the soundness of the code goes, is the following intuition, which is that for any code, classical or quantum, you can draw this sort of bipartite graph between the qubits on one side, the physical qubits, and the checks. You just draw an edge whenever that check participates non-trivially on that qubit, and you have this bipartite graph. And you'd say something is a epsilon small set expander if the number of checks that use the qubit that use qubits from S is like roughly the optimal size. So the optimal size would be the size of S times the degree. And then, if you add a little 1 minus epsilon, it's like roughly epsilon optimal. Okay. The problem is that if you have this sort of optimal expansion, then you get that in sets S, you look at gamma S, there's most of the points actually have a unique neighbor on the other side. And unique neighbors are bad in the case of quantum error correction, because what I'll claim is that it lets you construct a large error that violates few checks, which is exactly the worst case for a quantum LTC. And the idea is that you have the checks of the code, they commute on the code space. Let's just for a second say they commute everywhere. You really only need them to commute on the code space, but all the examples of codes we construct so far, they commute everywhere. And if they commute everywhere and you have a bunch of checks that only overlap on a single qubit, like so you have checks I, where these checks, they only intersect on this one qubit. Then there was this nice result long ago by Bravi and Viali, which said that morally that qubit is acting classically. That qubit can't be quantum if the checks don't overlap in a non-trivial manner. So if checks only overlap on one qubit, then there must have been a classical way to assign the value of that qubit. So then you end up with you just have these very simple either you have classical states, which we know can't exist for error correcting codes by the local indistinguishability argument, or you have terrible soundness. So it's like this catch-22 that occurs. Okay. I guess how much time do I have? Do you know?
5 minutes.
5 minutes? Okay. So let me just say a few large things that I recognize that as we get to the terminus of this talk, it's getting more and more technical. But you could say okay, well, Chinmay, what if you just imagine that you had QLTCs? Does that get you anything? Like just from the simple assumption of their existence, you're able to say all those things about quantum error correction just from their properties. Now, if you just assume QLTCs, what would that give you? So where were classical LTCs used? Well, one example is they were very pivotal in the construction of PCPs. So you could ask, is a quantum analog the case? Can you take quantum LTCs and you could construct PCPs directly? And it's not so clear. And the reason why you might think that is, well, what is the PCP theorem? If you're in an elevator and you have to explain it to someone, you might say that you just take an NP witness, like the solution to a 3-step formula, and you just wrapped it up in a really, really nice error correcting code with some locally decodable LTC that you wrapped it up in. It's more technical than that, but that would give someone a pretty high level explanation of how it works. One example is that you could just take your solution to your 3-step formula and you could encode it in the exponentially long PCP for the Hadamard code, right? And that would work. It would be exponentially long, but that's the rough intuition. What's the problem is that you couldn't do this same sentence for quantum PCPs because the quantum codes can't have good distance and be locally distinguishable. The whole point was that you wrapped it up in this code and you protected against errors and noise and adversarial noise all in one time, but you also still maintained local decodability, which let you extract out the values. If you wanted to do all that with your quantum error correcting code, well, then locally you can't find the values. So it doesn't even seem clear how to create an exponentially long quantum PCP, even if you had some black box quantum LTC. So even that's sort of wide open. So what are quantum LTCs good for? I'm not exactly certain. Other than they might be like a fantastic mathematical object to try to build, it's not exactly clear if they have a complexity use directly. But trying to come up with an argument that says, if I had a quantum LTC and could create a quantum PCP, that also is a very interesting open task that we don't know if it's true or false. So I'll just say that hopefully there'll be more to come in some workshop. in the middle of March. But with that, I'll end and take any questions.
So the explanation along QLTC is still.
Yeah. QLTC of any qubit to encoding rate. So the rate question, yeah, even rate 1 size n is open. So that would be like an exponentially long under reparameterization.
On that note, I mean, is it, what if your distance, what if you're not going to be good against constant fraction errors with much smaller errors?
Oh, like constant size errors? Yeah, so then there was this construction, where was it? Here, this one. Either of these two. They're both in the same paper, where the soundness was constant, but the checks were constant, but the distance was also constant. So maybe that could be used in some.
Squared in comes up a lot in these reasons. There's a squared in kind of thing that you might say you could get squared in
Distance. Yeah, I don't know too much about this. If there have been any papers that express this. There was this paper here by Leverrier, Lond, and Zemore, where the distance did come out to be root n, and the checks were even logarithmic size, but the soundness was only inverse logarithmic.
So this whole impossibility argument on the locality seems to hinge on the information theoretic argument. So if you encode k copies of the same state, would it go around this argument?
Possibly, but if you have k copies of the same quantum state, then what you'd hope is that I can get the measurement of some 2-qubit observable by taking qubit 1 from copy 1 and qubit 2 from copy 2, but that measurement is not going to give you anything, right? Because those are unentangled. So sort of how to take the measurement property that you might want, which is qubits 1 and 2 from the initial copy, and now extract that measurement from multiple copies is not clear either.
Yeah.
All right. Thank you.